Hello again. We are starting chapter 7, techniques of integration. Before we even look at 7.1, which is integration by parts, I would like us to review and also discuss few integrals that we have not presented or discussed in Calc 1. So first of all, I would like us to carve in stone or discuss the following. When we're asked to integrate e to the x dx, we know the answer is e to the x plus a constant c. But what if I have a situation in which I have the integral from 3x dx? All that is e to 3x divided by 3 plus a constant c. How come, and how can I check? Very simple. You differentiate e to 3x over 3 plus a constant c, and you have to get e to 3x. If you don't, then this is incorrect. And of course we do, because when we differentiate e to 3x, we get e to 3x times 3 divided by 3, and these two go away, and the constant prime is 0, so we get back e to 3x. Always very easy to check indefinite integrals. For indefinite, I can always check by differentiating both sides. When I differentiate an integral, I get the function, as we know from Fundamental Theorem of Calculus Part 1 from Calc 1. And when I differentiate the other side, we already show that here, that this is indeed e to 3x. Okay, so that's one thing I wanted to discuss. Then the second thing is, very important, 1 over x prime equals negative 1 over x squared. And when we integrate, for example, 1 over x squared dx, the answer is negative 1 over x plus a constant c. Of course, if we have negative, integrate negative 1 over x squared dx, then we get 1 over x plus a constant c. It starts with this. Number 3. For sine, cosine, or trig functions in general, for sine and cosine for now, the integral from sine x dx, we know, is negative cosine x plus a constant c, because if I differentiate this, cosine prime is negative sine with minus, and it gives us sine. And the other one, cosine x dx, we know this is sine x plus a constant c. When I differentiate sine, I get cosine. Now, what happens if, that is my page 2, what happens if I have the integral from sine 3x dx? Exactly the same thing as we had with e to 3x. So this will be negative cosine 3x divided by 3 plus a constant c. When you differentiate this, negative cosine prime is negative sine with minus in front, so it's sine 3x times the inner function prime, which is 3, which simplifies with this, and that's how we get that back. Of course, if I have the integral from cosine 2x, for example, this will be sine 2x divided by 2 plus a constant c. So I wanted us to carve these in stone, which are extremely important, these 3 items. So now, there were a few integrals that I personally did not discuss in Calc 1, and they are trig, so these two are very clear. But what happens if I want to, let's say, integrate tangent x? What do I get? What if I want to integrate cotangent x dx? What do I get? And of course, the other ones, the secant x dx and the cosecant x dx. Also, I wanted to discuss 2 more in addition to these 4. The integral from 1 over x squared plus a squared dx, and one more, 1 over the square root of a squared minus x squared dx and see what these are. So I would like us to establish the process for these, and then you can carve them in stone. You can put them in a table, and I do have prepared, and I did post the table of integrals, and this is in your book, and I also posted, I scanned all this and you can directly go to it. So you have algebra, you have geometry, all these are posted in each module, okay, and differentiation rules as well as table of integrals, and we're going to discuss these when we get to the tables. Okay, good. Okay, moving on. So let's start with tangent and then cotangent, secant, cosecant, and then these two. And then we can say that we exhausted the preliminaries and we can start section 7.1. So that's the idea. That's what I'm trying to do now. So let's start with tangent. So I'm not asking you to determine or memorize the proof, but I think it's useful to see it at least once. So the integral from tangent x dx, of course, is the same with the integral from sine x over cosine x dx. Very easy to use a substitution from chapter 5. And obviously, I will use u equals cosine x. Remember what we need? We always need du, which is the differential of u, which is negative sine x dx. Yes, you can solve for the x, but really it's not a big deal. I'm only missing a negative sign. So if I multiply by -1 twice, this is too easy to work so hard and determine the x and put it in and so on and so forth. That's my opinion. You can use other methods. So basically this is du and this is du. So all we have is negative the integral from du over u. And we know that this is negative natural log of the absolute value of u plus a constant c, which is nothing else but negative natural log u is cosine x plus a constant c. We know one of the properties of natural log is the power property. So that whatever number I have in front, I have in front of natural log is basically coming from the power of the expression log is applied to. So this is the same with, okay, page 3, natural log of the absolute value of cosine x raised to power -1 plus a constant c. But we know, there's a side note, that we know that cosine to power -1 is 1 over cosine x. This is not the inverse function, careful, but 1 over cosine x is the same with secant x. So then I continue, natural log of the absolute value of secant x plus a constant c. So now we know what this equals to. And from now on, you either use the table or have it handy, but now you know that the integral from tangent x dx is natural log of the absolute value of secant x plus a constant c. Moving on to cotangent. So the integral from cotangent x dx, of course, is the same with cosine x over sine x dx. From chapter 5, we're going to use a substitution. Let u be sine x. Of course, the differential has to be there. Cosine x dx. It cannot be easier. So this is the integral from du over u. And that is natural log of the absolute value of u plus a constant c, which is natural log of the absolute value of sine x plus a constant c. So moving forward, we know from now on that the integral of cotangent is natural log of the absolute value of sine plus c. Moving on to secant. The integral from secant x dx. Well, secant, the integral of secant has a little bit of a trick to it to find it. And here's the trick we are going to apply here. Secant x. We're going to multiply and divide by the same quantity, which will not make any difference or any change. This will be 1. But the quantity we need, which is the same, of course, has to be secant x plus tangent x, secant x plus tangent x. You'll see in a moment why. I will distribute secant, so I get secant squared plus secant tangent divided by secant plus tangent dx. And now I will let u be this quantity, secant x plus tangent x, and of course du is secant prime, secant tangent, tangent prime, secant squared, of course dx. And look at that. This is exactly what I have here. So then I have the integral from du over u. I squared it, put it in a little box, so you know it continues here, jumping over all this. Okay, so then we have natural log of the absolute value of u plus a constant c, but u is all this. So this is natural log of secant x plus tangent x plus a constant c, which tells us that we already have secant x. We're moving on to cosecant. For cosecant, we're going to use the same technique as before. So this is the integral from, cosecant x and multiplied by, I meant to write cosecant x plus cotangent x, of course dx, same quantity, no change. So of course I will distribute. So cosecant squared x plus cosecant cotangent divided by cosecant x plus cotangent x dx. Of course, this is the trick. U equals cosecant x plus cotangent x, of course, dx. I didn't mean to do that. I'm not there yet. Sorry. Okay. Now du. Cosecant prime is negative cosecant x cotangent x, and cotangent prime is negative cosecant squared x, of course, times dx. And you can notice now that this is the same quantity but with minus, and this is the same quantity with minus. No big deal. I will multiply by -1 twice. Once here and once in front. Once here, once in front. -1 times -1 is 1. Okay, so then we have negative in front. All this at the top is du. You know the drill now. The denominator is u, so the whole thing is negative natural log of the absolute value of u plus a constant c. I will have to replace u by this. Cosecant x plus cotangent x in absolute value plus c. Of course, you know the -1 goes, it's coming from the power of the absolute value. No big deal. This is good enough. It's fine. But in order to show what the table of integrals presents, I'll show you the next steps. So natural log cosecant x plus cotangent x to -1 plus a constant c. Okay, so now let's look at a note. Cosecant plus cotangent raised to -1 is 1 over cosecant x plus cotangent x, which is 1 over cosecant is 1 over sine x plus cotangent is cosine x over sine x. They have the same denominator. I will flip. Let me move this out of the way. So I have sine x over 1 plus cosine x. And I'm sure you remember this little trick from trig. 1 minus cosine x, 1 minus cosine x, same thing, no change. But when I multiply these two, I get 1 minus cosine squared x, which is sine squared x. So then sine times the numerator, but everything divided by sine squared. This was sine x, careful. So we remove one factor of sine x, so then I have 1 minus cosine x over sine x. Since the denominator is one term, I can separate this expression into two fractions, into 1 over sine x minus cosine x over sine x. This we know is cosecant x. This we know is minus cotangent x. And all this exercise was just to remove this negative power. Okay, so then from here, I'm going to use a triangle this time, jump over everywhere, all this, and get here. And the answer is natural log of the absolute value of cosecant x minus cotangent x plus a constant c. Okay, so let's see how we are on time. Okay, so where is my first page? Okay, so this is done. Now I would like to discuss these two. So let's take a look. And then we can finally start 7.1. Just to make sure. So I'm on page 6. Page 6. Okay, and we're looking at the integral from 1 over x squared plus a squared dx. So we looked at these four. Now we're here, and this is the last one. And then we'll start 7.1. Because these are basic integrals and we need to know them. So in this particular case, I will factor out by force, if you want, a squared in the denominator. So then what I have now is x over a everything squared plus 1 dx. Okay, so how did we do this? So x squared plus a squared, if I factor out a squared, then I have x squared over a squared plus 1. Let's check. This times this is x squared because I simplify and I get x squared. And then x squared times 1 is a squared. That's how I got this. Now I will say let u be x over a. And of course du will be 1 over a dx. So now let's see what happens. The equal symbol, I continue here. The numerator, the number in front is 1 over a squared, but I really need 1 over a with dx. So I'm going to keep 1 over a in front, but I will connect 1 over a with dx. So 1 over a, 1 over, I'm going to write it as is for now so you can see, times dx over a. So I have a times a, which is a squared. Same thing, I just wanted to have it separated because now this will be replaced by du, and this will be replaced by 1 over u squared plus 1. So we continue. 1 over a, 1 over u squared plus 1 times du. And I know what this is. It's 1 over a arc tangent u plus a constant c. We have to replace u by x over a. 1 over a arc tangent x over a plus a constant c. So now you know what this is. So 1 over x squared plus a squared is the same with x squared plus a squared is 1 over a arctangent of x over a plus a constant c. And here's the last one. The procedure will be somewhat similar. Okay. So for the last one, we have 1 over the square root of a squared minus x squared dx. So the same thing, I will factor out a squared. So I have a squared minus x squared, which is a squared 1 minus x over a everything squared. Oops. Okay. Just making sure. I don't care about that. I care about this. Okay. Good. So in the same way, when I apply the square root, then we get the square root. Let me put the equal symbol here. Just to make sure for those who have never taken my class, this does not mean they're two equal symbols. It only means that the problem does not finish here, does not end here. Look for the equal symbol because something follows. Okay, so then we have 1 minus x over everything squared. So I'll continue with this, and I'm on page 7. So the integral from 1 over the square root of a squared minus x squared dx is the same with 1 over the integral from dx over the square root of 1 minus x over everything squared. And like before, we are going to use a substitution. So any letter, it doesn't matter. X over of course, du equals 1 over dx. And we move on. And the dx with the I already have it, is the integral from du over the square root of 1 minus u squared. And we know what this is from a long time ago. So this is arc sine u plus a constant c, which is the same with arc sine of x over plus a constant c. I hope this helps, and the next video will present 7.1.